earlier in the semester, we went from linear kinematics, basically just the study of motion, to linear dynamics, which is the study of forces on an object, right? How forces can sum on an object and result in the change in motion of that object, right? Basically, Newton's second law, okay? Now we're doing the exact same thing for the rotational world. We're going from rotational kinematics to rotational dynamics, which basically just means how do you use Newton's second law to analyze the motion of objects that are rotating as well as moving in a line or translating, okay? And so the bright side of that is, again, you know the foundational principles of this. There's not going to be a lot new here. We're just adding in, instead of just a sum of forces, we're adding in a sum of torques that act on any given object, okay? Because to truly be in equilibrium, not only do you need to have the sum of forces on an object to be zero, but the sum of the torques on any object also needs to be zero. And we're going to talk about what that means in this chapter. But first of all, as always, why do we care? This chapter truly, I think, is one of the most important chapters for anyone who's trying to keep the physical body healthy and working properly. This chapter is especially important for physical therapists and people getting an intuition for how different things can impact the body and how to prevent damage to the body through different repetitive motions, especially if you're someone who has a high impact career that affects the body, or that you're involved in sports or something like that, okay? And so this why do we care relates specifically to this concern about how to maximize the health or understand the effect of torques on the body. And one way in which torques really affect the body is when somebody's working out, right? You have, weights that are applying a force at a certain distance from an axis of rotation, right? That is a torque. And we need to pay attention to that in order to find out ways in which to minimize the potential for injury and the potential for long-term wear and damage to the body, okay? So you guys can see it on this slide, the physics of pumping iron. I'm not going to read this whole thing. I will just let you know that we will be able to analyze situations where there are torques in the human body and solve this problem involving this fellow with the deltoid muscle and the dumbbell, okay? Next, I would like to revisit equilibrium. If you remember, back in the day, we used to say that equilibrium meant that the sum of the forces in x equals 0 and the sum of the forces in y equals 0, okay? So in other words, let's say I have some object, right? Right? Some blob. And we need to know that the sum of the forces in x and the sum of the forces in y must equal 0, right? But what happens if there's a force, let's say here, that makes the blob want to rotate about an axis here, okay? If there's some force here, that's going to make this blob accelerate, have an angular acceleration around in a circle, just like we talked about last week, right? But an angular acceleration, a rotation in a circle, is still not equilibrium, right? The object is not stable. The object is actually accelerating about this axis, okay? So true equilibrium also means that the sum of torques acting on an object must also equal 0. So really, you can think of this chapter as the force chapter that we already studied, and I believe that was week 6, right? But adding this one extra component here, that the sum of torques have to equal 0 as well. And so it's probably a good time then to kind of revisit what torque is, okay? And so as this picture shows in this slide, what is torque? I have a little, you could think of it as like a little axis point that rotates, right? And then we have a little bar out here, okay? And then we have a force that's being applied to it so that it rotates in this plane, okay? So I put a force there, and it's rotating in this plane. So if there's a distance r away from this axis of rotation, right, then the torque, and so I just want to try to be clearer here. This force is in this plane, right? It's going into the board, whereas this torque is going literally up, okay? So R and F are in this plane, and torque is going up. So basically, this force here will make this want to rotate in this circle, right? And so the interesting thing about the torque is it's a vector, and the direction of that vector is always perpendicular to both R and F, okay? So I'm going to start by saying that the formula for torque is equal to R cross F. This is why we study the cross product. But we can really simplify it, because I think you guys probably remember R cross F is really RF sine of theta, okay? So to find the direction of the torque, all right, it'll always be perpendicular to the plane made by R and F. So if R is here, F is here, right, torque is going to be perpendicular to that. And there's this thing called the right-hand rule, which is going to come up a million times over and over again in physics, but we'll start it here for the first time. And this right-hand rule says, if you're doing any kind of a cross product, you put your fingers in the direction of the first vector, right? So this R here is a vector. It points away from the axis of rotation, right? And F is a vector. So R is pointing in this direction, and I encourage you guys to follow along in the video. R is pointing in this direction. Then we curl our fingers in the direction of the other vector. So if F is here, right, trying to make this thing rotate, it's pointing in, I'm going to curl my fingers in that direction, which means that my thumb then is the remaining vector that points in the direction of torque. So R cross F gives us our torque. And now you might be like, well, I don't understand. The force is in this direction. It's making this thing rotate. Why would torque be up? So one way to think of it is that if this were a bolt, okay, and you applied a force in that direction, you'd be unscrewing that bolt, and the bolt would come up, okay? The threads on screws are actually designed to follow the right-hand rule, okay? So you just do what they do, right? Lefty-loosey, righty-tighty, or whatever it is, okay? So R cross F gives you your direction of your torque. And so the torque will be in the positive Z direction, okay? So like this would be the X, or the I direction, this would be the J direction, and this would be the positive Z direction. Okay? All right. So if you go to the next slide, this just reminds you that R cross F is really RF sine theta, which you guys are a pro. You guys know that by now. The next thing that I want to be careful about here is sign conventions, okay? So what makes a positive and what makes a negative torque? Okay, and the truth is that forces that make an object want to go counterclockwise, so in other words, this way, all right, that will be a positive torque, all right? And then forces that make an object want to go clockwise, that's going to be a negative torque. And I want to point out in these slides that there's a mistake that I'm noticing right now. For forces that make an object want to rotate clockwise, that should be negative. So don't let that fool you, okay? So what direction would this be, a positive or negative torque, this force acting on this object? Well, if this is my axis of rotation, right, and I have a force here, this guy would want to move counterclockwise. That would be a positive torque, okay? Let's suppose that I apply another force over in this direction, though. So we'll call this force 1, we'll call this force 2, right? Now, if my axis of rotation is this way, and I'm applying a force here on my blob, right, this thing will want to rotate this way, right? Which would make this be a negative torque because that's clockwise. So F2 would make this guy want to rotate clockwise. F1 would make this guy want to rotate counterclockwise. Counterclockwise gets a positive torque, and then clockwise would get a negative torque. Okay? Just one more quick example. Let's say that I have this object. It is a bar with a little pin in the middle of it, and I apply a force right here to it. Would that be a positive or negative torque? Well, if I have this pin down and I put a force here, this is going to want to rotate clockwise, so that would be a negative torque. Okay? You get the idea? What if I put a force here. Take a moment to decide. Well, if I push down here, again, this thing will want to rotate clockwise. That would be a negative torque, right? If I applied a force down, that would want to rotate counterclockwise. That would be a positive torque. All right, I hope that makes sense. So looking at your torques, you can tell it has a lot to do with how to create stability in different objects. Okay, this is something that, especially if you're in civil engineering or architectural engineering, it's very, very important to study and make sure your torques maximize the stability of an object instead of minimizing the stability of an object. And so if you look at this example where you have a bunch of dominoes versus a big block, okay, in the case of those dominoes, any slight movement, right, any slight movement, so remember the center of mass, the center of gravity acts on the center of an object, right? And so since that's a force, if there's an angle, then suddenly there's going to be a torque, and that thing is going to want to fall. That's why dominoes fall, right? It moves a little bit, as you can see from this picture. Here, I'll do it right here. If a domino even moves just a little bit, you have a force due to the weight, right? That's at some angle, right? And that weight times that distance times sine of that angle is a torque that's trying to rotate that domino, and the domino then falls. Okay? But if you have a big block over that, like that, it's not as easy to get this to turn just a little bit one way or the other. And so the big block ends up being much more stable because you don't have a theta, right? Theta ends up being 0, and then torque is 0, and there's no torque. Okay? So building stable structures, whether it's a building or the human body, or like even advice that you give people in sports when you're, I don't know, say in football when you're tackling somebody, right? This involves using, in martial arts too, using torques in such a way to maximize your effectiveness, okay? Whether it's the stability of buildings or how to make sure that you stay stable in any kind of an altercation in the case of martial arts, okay? In the next video, we're actually going to start calculating for torques using the human body in a couple examples, all right? I'll see you there.